Japan has been building this for 60 years. Most people have never heard of it.
Japan has built a train unlike any other. It floats mid-air and moves at speeds up to 370 miles per hour. That's faster than any other land vehicle in the world. Not only that, but this project costing billions cuts straight through mountains to create some of the most advanced tunnels ever built.
The geology under the Southern Alps is 300 million years old, and unlike anything engineers had tunneled through before.
The roughest terrain, an exploding budget, and bureaucratic nightmares, this project has survived them all. Let's get right into it. The fastest train. The year is 1964, and Japan is scrambling to prepare for the Tokyo Olympics. And the biggest issue they face is their slow subway infrastructure. The solution? Build the Tokaido Shinkansen, the world's first high-speed railway line that reached speeds up to 177 miles per hour during normal commute. This new railway line was the first of its kind. Its insane speeds baffled the world, cutting the travel time between Tokyo and Osaka from 7 hours to 4 hours. Later, that was further cut down to just 2.5 hours. No other train in the world came even close to matching that. Because of that, the Tokaido Shinkansen has become an essential part of Japan's transportation systems over the last 60 years. Millions of people use it every single year. But there is one huge problem. The once fastest train in the world is now failing to keep up with the growing population and tourism in Japan. The line isn't just for commuters. It also transports cargo, adding extra pressure from the added traffic. Because of that, despite being the most frequent and busiest lines in the world with 17 trains operating per hour, the Tokaido Shinkansen is just not enough anymore. Fearing that the backbone of the Japanese transportation system would be overwhelmed, the government looked to experts for a solution, and what they proposed was mind-blowing. They wanted to build a train so fast it would break all records, create an alternative route to relieve pressure on the Tokaido Shinkansen line, and propel Japan's transportation infrastructure decades ahead. And so, the Chuo Shinkansen Maglev was born. Chuo Shinkansen is a proposed new route for a maglev train that would run between Tokyo and Osaka at speeds of up to 314 miles per hour, nearly twice that of the Tokaido Shinkansen line. At those speeds, it will be the fastest-moving vehicle on land in the entire world. It would be even faster than most commercial planes and most fighter jets we have today. But building something of that scale is not easy. It involves scientific breakthroughs, billions of dollars in investment, and a commitment unlike any other. And the first step in achieving that dream was building the Chuo Shinkansen Maglev. A Chuo Shinkansen Maglev is as different from a standard train as a modern smartphone is from one of those old dial phones. And the difference comes down to essentially how it moves. For a standard train, the process is quite simple. There is a track and the train runs on it using steel wheels. Now, for the longest time, experts tried to make these trains as fast as possible by improving the physics involved. They improved the aerodynamics of the train, reduced its weight, and even redesigned the tracks to be smoother. But all that only went so far before the scientists ran into their biggest enemy: friction. No matter what the experts did, the friction between the track and the train wheels diminished the speed increases, maxing out the fastest trains to about 250 miles per hour in ideal conditions. With no other way forward, a new idea was born. What if this friction is completely eliminated from the system? The only way of going about doing that is to eliminate the contact between the train and the tracks. From this proposal, the maglev train was developed, which would become the backbone of the Chuo Shinkansen project. A maglev train doesn't primarily run on wheels. Instead, it floats mid-air, levitating above the track at the perfect height. With no direct contact with the track, there is no friction to deal with. But how did the scientists achieve this? Behind each maglev is a complex electromagnetic system that makes this unique way of transportation possible. For the Chuo Shinkansen maglevs, the levitation is achieved using a technology called superconducting magnets, which are installed on the underside of the bogies where the tires usually go. When cooled to extremely low temperatures, These superconducting magnets have near-zero resistance. This allows for electricity to pass through them without turning to heat, resulting in very powerful electromagnetic waves. This process is what makes the Chuo Shinkansen different from the Maglevs used around the world. Through the use of superconducting magnets, the Chuo Shinkansen Maglev can achieve a levitation height of nearly 4 inches. Standard Maglevs, on the other hand, only levitate by about a centimeter since they do not utilize superconductors, relying solely on conventional electromagnets for levitation. But the engineers didn't stop there. They developed a unique shaped channel for the Chuo Shinkansen Maglev that acted as the train tracks. These channels aren't just for show. They have 2 sets of coils embedded within their walls that act as the propulsion system for the Maglev. While the electromagnets in the Maglev make it float, these coils lock onto that and precisely manipulate the electromagnetic fields to drive the Maglev forward. So in a way, the engine isn't on the Maglev itself. Rather, the tracks are the engine creating the extreme movement these trains are known for. There are a couple of things that make the Chuo Shinkansen's track unique. First, it makes derailment impossible. The U-shaped channels encase the Maglev's bottom area from 3 sides, locking it in place once installed. Plus, the higher levitation height of the Chuo Shinkansen Maglev means that it has more room to adjust in case there is an earthquake. This was done intentionally since Japan is prone to earthquakes. But developing the basic technology behind the Chuo Shinkansen was just the first part. Engineers work hard to expand upon this tech to make it one of the fastest and safest trains in the world. Testing for success. With the basic technology for the Maglevs developed, Japanese scientists took to the test tracks to make it even better for the Chuo Shinkansen. In the 1970s, the Miyazaki test track was built, which would become the backbone of the project. Spanning 4.3 miles, it became the research ground for the early concepts of the Maglev trains running at higher speeds than the commercial version at the time. In 1979, the ML500 made a world record on these tracks, achieving a speed of 321 miles per hour, faster than any other commercial Maglev at the time. However, the limited length of the Miyazaki track soon became a problem. To resolve this, a new track was made in Yamanashi Prefecture, spanning 11.4 miles. And this is where history was made. Experts got to work turning the outliers into the norm. Maglevs regularly achieved speeds of over 300 miles per hour as the technology involved was improved further. Public from the region, as well as government officials, took part in the test by riding the Maglevs on the test runs, providing further data on their performance. Later on, the Yamanashi track was extended to be 26.6 miles, allowing for even longer test runs. Soon, Japanese engineers were breaking record after record. In 2003, an MLX-01 reached 361 miles per hour, breaking the record set on the Miyazaki test track. Engineers also ran 2 trains in opposing directions to achieve a closing speed of 637 miles per hour. Based on these studies, experts developed the L0 series Maglevs, which will be the trains used for the Chuo Shinkansen project. At 981 feet long, the L0 Maglevs can board up to 728 passengers at a time. For commercial use, they are designed to operate at a speed of 310 miles per hour. But on the Yamanashi track, the L0s have achieved speeds of 367 and 375 miles an hour, breaking all previous records, making them the fastest trains in the world. The testing process is still ongoing. Newer and newer technology is being deployed on the tracks every day to further refine the Maglev technology. Not only that, but experts have been modifying the track to make it as close to the Chuo Shinkansen's route as possible to ensure each train that passes through is designed specifically for the needs of the project. As a matter of fact, the Yamanashi track is part of the Chuo Shinkansen route, so it will be incorporated into the actual train line once the routing is finalized. But figuring out a route for such an important line is no easy task. Routing and construction. The route selection for the Chuo Shinkansen project had to be precise and carefully thought out due to the unique challenges that Maglevs pose, especially those traveling at such extreme speeds. Maglevs don't handle curves in the track too well. They need to slow down for these turns, and that defeats the whole purpose of the Chuo Shinkansen, which seeks to be a faster route from Tokyo and Nagoya compared to the slower Tokaido Shinkansen. So the route has to be as straight as possible to ensure the Maglev can maintain its top speed for as much of the route as possible. This is easier said than done, however. The first concern is connecting major urban hubs. Cities don't tend to line up perfectly in a line, and that is the case for Japan as well. So the government officials had to choose between connectivity and speed. Experts debated over which cities should and should not be connected. In the end, the route planned out was pretty straight, only connecting cities that are essential, including Tokyo, Nagoya, and Osaka, making it much more direct than the Tokaido Shinkansen route. But this came at a huge cost. The route that experts proposed cuts directly through the Japanese Alps, and one thing mountains don't allow for is straight routes through them. Trains usually have to climb up the mountain using sharp turns to cross it. But since that isn't an option for a high-speed maglev, experts had to come up with a new strategy. Instead of climbing the mountains, they would dig straight through. The Chuo Shinkansen section between Tokyo and Nagoya spans 178 miles, and of that, nearly 90% is going to be underground tunnels. This will include the Southern Alps Tunnel, which, once completed, will become the deepest railway tunnel in all of Japan. Digging through the Alps means that the maglev can run in a straight line even through the mountainous sections. But that in turn creates complications of its own. Building overland is simple. Lay out a track and let the trains run. But in tunnels, it becomes much more difficult. The first problem you have to face is the tunneling process itself. For the most part, tunnel boring machines worth millions of dollars have to be made or imported from countries like China. Then these machines have 2 or more workers day and night to dig through solid rock to create the tunnel. And where that is possible, humans have to dig themselves using machines, tools, and sometimes even explosives. Besides the risk posed by that, there are constant safety concerns during the tunneling process. Cave-ins are a constant threat if the tunnel walls give out or a natural disaster like an earthquake happens. Tunnels can get flooded pretty easily from water infiltration. And the biggest problem of all is that you are digging through relatively unknown geology. While surveys and scans do provide some information about what's ahead, threats can be lurking anywhere. The ground can get too soft or too hard. Unexpected water aquifers can be breached by accident. There is so much unknown involved. But since Japan has so much experience in tunnel boring, engineers are confident they can navigate the dangers and successfully dig out the Chuo Shinkansen route. But at the same time, they also have to resolve another problem that tunnels pose for high-speed maglevs, and that is the piston effect. The L0 series reaches speeds over 360 miles per hour, and to move at such speeds, it needs to push out the air in front of it with much more force than a standard train. Now, above ground, that tends not to be such an issue. The air spreads out and moves out of the way. But in a tunnel, there isn't much space for the air to go. The walls of the tunnels hinder that movement. The train pushes ahead, but the air doesn't get out of the way as effectively. This causes increased drag on the train, causing it to slow down. This is the piston effect, which is a huge headache for engineers working on the Chuo Shinkansen project. So the engineers have to get creative. To prevent the piston effect, the tunnels have to be designed much wider. This gives the air more space to disperse. Additionally, pressure relief shafts are built at important points to allow air to escape the tunnel when a maglev is passing. This way, the built-up air pressure doesn't end up damaging the tunnel's structure. On top of that, the noses of the L0 series maglevs have also been made longer and more aerodynamically shaped compared to normal maglevs. That way, they can pierce through the air more effectively, like a knife, instead of ramming into it with a flat nose. This design choice allows for much less air to be compacted in tunnels, even when traveling at extreme speeds. But the piston effect was not the only major challenge for the Chuo Shinkansen project. Another place where Japanese engineering shines is the Shinagawa Station. This station is going to be an important stop for the Chuo Shinkansen route, and it has to be built completely underground. That's because the entire station is going to be built underneath the existing Tokaido Shinkansen station, a busy platform used every day by tens of thousands of people. Naturally, the operation of the Tokaido Shinkansen station cannot be disturbed for the construction of the new station beneath it. So the construction has to be done in such a way that everything above keeps running smoothly. Due to the extreme complication of such a task, the construction process for this station alone is going to take 10 years, according to experts. While all this goes to show the ingenuity of Japanese engineers for figuring out solutions to such complicated problems, that doesn't mean the project has been safe from its share of controversy. The Shizuoka crisis. While most of the route for the Chuo Shinkansen is already under construction, there is one span that has been left untouched. About 3% of the route runs through the Shizuoka prefecture, and the officials in charge of the prefecture have adamantly refused to allow the construction of the line. Their reason? The Oi River. The Oi River is a vital source of water for the region, used extensively by the local population and for industrial needs. The municipality has stated that the Chuo Shinkansen is being built far too close to the river. There is a risk of the river leaking into the tunnel, dropping the water levels of the river, and creating a huge issue for the locals. The infrastructure in place for the river could get disrupted, and many could go without access to water. Certainly not a promising outlook, but according to some, that is not the only reason why the officials are so against the Chuo Shinkansen line. Allegedly, they have a hidden motive. You see, while the Chuo Shinkansen line is going to run through the Shizuoka prefecture, it isn't going to have a station there. So, the prefecture is going to have to deal with extensive construction and all the hassle that comes with it for the line, and nothing good really happens for the public in return. No access to high-speed maglevs, no ease of transportation. That didn't seem like an equal exchange to the officials, so they refused collaboration, preventing this small portion of the line from being built, bringing the project to a complete halt. According to the officials, they don't even want a station from the Chuo Shinkansen line specifically. They are happy with just another station being built for the Tokaido Shinkansen line. In the end, however, this tactic didn't work out. Huge projects like these with the backing of the government don't get stopped so easily. In 2024, the governor opposing the Maglev, Heita Kawakatsu, resigned. The next elected governor, Yasutomo Suzuki, was more open to the idea. He agreed to allow the construction to continue in exchange for the prefecture being paid compensation in case the water levels of the Oi River dropped for whatever reason. Still, the delays have caused some damage already. The initial expected date for the completion of the project was 2027, but due to delays and unexpected complications, that was pushed to 2037 for the full line to Osaka. The steep cost. Now for the big question. How much is all this going to cost? Well, the Chuo Shinkansen line involves a lot of very expensive projects within its umbrella. Digging the tunnels needed for the route required billions of dollars. And then there are the trains, which also required a lot of money to build and develop. It is a mega project in the true sense. According to experts, the entire thing is going to require nearly $82 billion to complete. But those are still early estimates. As the construction continues and more complications arise, that number will probably increase. So is it worth it? Can paying such a huge bill really benefit Japan? The simple answer is yes. Japan is a country that invests in itself. It isn't one of the biggest economies in the world for no reason, and transportation is something that boosts the economy in more ways than just ticket sales. First, let's take a look at numbers. Today, it takes an hour and 26 minutes to go from Tokyo to Nagoya on the fastest bullet train available. The Chuo Shinkansen will cut that travel time to just 40 minutes. Traveling from Tokyo to Osaka takes 2 hours and 30 minutes. The Chuo Shinkansen will reduce that to just an hour and 7 minutes. Those are huge gains, and they have a direct impact on the country's economy. With the connectivity between some of Japan's biggest urban centers boosted by the new line, people have more opportunities available to them. Businesses can operate between the cities more easily. Someone in Nagoya can find a job in Tokyo and commute there in a realistic amount of time. Tourists can visit these cities and spend money there. Things like these are what boost the economy and generate revenue in ways not directly apparent at first glance. But there is another way Japan is going to make money from this project. In building the Chuo Shinkansen project, Japan has achieved something no other country has. They have made the fastest trains in the world. And that is the kind of technology other countries want and are willing to pay a lot of money for. While it is not certain, it is likely that Japan will push to sell its L0 series trains and the accompanying infrastructure expertise to other nations that are also looking to improve their transportation infrastructure. Japan has already tried selling it to the USA, but that deal fell through. However, it is possible they could make and sell these trains to other interested parties for billions of dollars, boosting the economy even further. Especially since these maglevs require much less energy to function and can achieve speeds much higher than any other train in the world. That does it for this video. If you enjoyed watching, be sure to like, share, and subscribe. See you in the next one.